We are Team 8 within the CSE Senior Design Project Groups, and we will be sharing our IoT Energy Consumption Analyzer. Battery life of a product is a critical component of any device meant to be in the hands of consumers. Small changes in firmware can add up over time, resulting in a large loss of unexpected battery life, which leads to a poor customer experience. We've partnered with Triax Technologies to engineer a software solution that automatically tests new firmware, measures the power consumption, and compares it to a baseline.
We considered what needed to be flexible in our open source program. We provide the developer with a Python script that they call and with which they can track the process. The developer provides their device's firmware, the test script of their firmware's features, their choice of baseline file, and their choice of threshold from the baseline results. In terms of the analysis performed by our framework, it should be entirely configurable such that the user is able to choose what sorts of statistics to extract from the analysis in order to characterize their product's power consumption. These statistics could be average current, average power, or peak power. We also want to create a baseline against which we can compare the results of each of our test runs. This baseline should be computed from a configurable number of sample runs and should provide both statistical and fixed threshold suggestions that can also be configured by the user for the purpose of the analysis and comparison.
At first, we have focused a lot on the hardware variability of the project, which raised a lot of questions surrounding the modular of the solution would look like. We need additional hardware accessory to help transfer and collect the data to perform analysis on, starting with the multimeter, which monitors the electric current readings. One option for it was cathode model. Even though this device will provide the data needed, we decided against this option because it did not fit the open source nature of this project. The cathode device is thousands of dollars more expensive than the Nordic model that we decided upon and poses financial pressure on the user. We wanted our solution to accommodate for companies for all different sizes and developers with varying budgets.
Overall, we did not stray from the original vision that Triax had for the proposed solution. There is no CI platform functionality at this point, but we hope to explore this feature further given more time. At first, we did invest a lot of time into understanding the embedded systems programming to generate a baseline program on the TICC 2650 using their IDE, CCS. This program served as the firmware of the device, but we figured that we needed to concentrate on the development of our battery analyzer script, not necessarily the hypothetical firmware update. The user runs the script from their laptop with their DUT connected to a JTAG controller, using relays to help load the firmware without directly connecting to the computer, which could interfere with the sensitive readings. We wanted to move away from Nordic's Power Profiler program NRF Connect to localize everything onto the user's command line. Using the PPK2 API developed by ERNUS, a hardware development organization, we created a PPK2 wrapper that uses the framework from the imported library. It is able to recognize the connected PPK through serial and sets the voltage settings, such as the amount of voltage, along with where and how this electricity is being passed. Testing against the baseline generated from the previous firmware version of the DUT, we run 5 trials of the new update to see the average current usage and the differences that occur. The output is then returned in a JSON file to be saved to a user's desired directory.
Say that I am a developer at Triax Technologies looking to analyze the energy consumption of my Texas Instruments CC 2650 sensor tag. We want to test a new firmware that blinks an LED many times upon launch to gain the attention of the user. I connect my power profiling kit and JTAG and get ready to run my Python script. I locate the script main.py and call it from the terminal command line with our configuration JSON file that contains the firmware, test script, and analysis script. With the audible click, we know the JTAG is connected. The status of the hardware is printed in the terminal as our program runs. We watch the blinking LED, which indicates that our test script is being run. Upon completion of the test run, our program produces a CSV file containing the data from the run. This data is used in the analysis script, which produces a results file comparing the average current reading of the run to the baseline average current. If the difference between the two values falls within the established threshold based on the baseline, the test run is flagged as a pass.